So imagine you're standing on the roof of a 10-story building, right? And you drop a heavy iron ball off the edge.
Okay, I'm picturing it.
If you do that, standard physics provides a perfectly clean formula that tells you exactly when that ball is going to hit the concrete.
Right, yeah, you just plug in the height, you plug in the gravitational constant, and boom.
Exactly. The equation spits out a number,
Uh-huh.
and the result is just absolute. It's totally deterministic. You know exactly what's going to happen.
But, and I think this is where we're going with this, if you try to take those same, beautiful, precise rules of classical mathematics,
Yeah.
and you try to apply them to the global stock market, say to predict the price of a derivative or a portfolio, you will fail catastrophically.
Just a complete disaster.
Complete disaster, because you are essentially stepping out of a world of predictable physics and into a landscape of just pure, unadulterated chaos.
Which, honestly, is the entire core mission of our deep dive today. We are looking at how quantitative analysts actually pull this off. Like, how do they mathematically model chaos?
It really is a mathematical paradox, How do you build a concrete, reliable system that manages billions of dollars in global wealth when the underlying asset you're tracking is inherently random?
Right, because you can't just use standard engineering equations to measure noise.
No, you absolutely cannot.
So to figure this out, we're unpacking a really rigorous set of lecture notes from the certificate in quantitative finance. Specifically, we're focusing on a section called Stochastic Calculus and Ito's Lemma.
Which sounds incredibly intimidating.
It does. But our goal today is to translate all of that into plain English. We're going to figure out how to take pure unpredictability and translate it into concrete mathematical laws.
And the journey the text outlines is actually profoundly elegant because it scales from the totally mundane to the global. We're going to start with literally the simplest game of chance you could possibly play.
Flipping a single coin.
Exactly. And from that basic mechanic, we'll slowly build up the foundational equations that run modern algorithmic trading.
We're going to look at the math, but more importantly, we're going to understand the philosophical reasons why financial models are forced to operate this way.
Yeah, the why is a really fascinating part.
So let's start right at the foundation. We need a way to turn unpredictable randomness into something a mathematician can actually study.
Right.
And the text introduces a highly specific, motivating experiment to set the stage for all of this. We're looking at a simple coin toss game.
So imagine you sit down at a table to play, and the rules are totally binary and symmetric.
Keep it simple.
Right. Every time you flip the coin and it lands on heads, you receive exactly $1. Every time it lands on tails, you pay out exactly $1.
So it's the definition of a fair game, 50-50 odds.
Yep, perfectly fair.
The lecture notes actually provide a specific sequence of flips to ground the theory in reality. And I want to walk through this because it really helps.
Oh yeah, let's do the sequence.
The sequence they give is tails, heads, heads, tails, heads, tails. So THHTHT. Let's trace the actual wealth of a player walking through that sequence because it reveals something fundamental about how we track random variables.
Okay, so you sit down with nothing. Your starting wealth is 0.
Right.
The first toss is tails. You hand over $1, meaning your total wealth is -1.
Off to a bad start.
Yeah, but then the second toss is heads. So you win $1, bringing you back up to exactly 0.
Okay, back to even.
The third toss is heads again. So now you're pushing into positive territory. You are up $1.
Nice.
Then the fourth is tails, dragging you back to 0. The fifth is heads, putting you up $1 again. And the sixth and final toss is tails, dropping you back to exactly 0.
So after all that, you finished the game entirely even. You made nothing, you lost nothing.
Right. And to build a mathematical framework around this experience, the notes define a set of core variables. They start with the variable r sub I.
R sub I.
Okay. This represents the random amount of money you make on the ith individual costs. So, looking at our game, r sub I only ever has 2 possible values. It's either a positive one or a negative one.
Because you either win $1 or lose $1. Simple enough.
Exactly. And because we're dealing with a perfectly fair coin, we have to look at the expected value of any single toss. Mathematicians write this as E bracket R sub I.
An expected value is basically just What you'd average out to if you played forever.
Exactly. It's the average outcome if you played the game an infinite number of times. Half the time you get +1, half the time you get -1.
So they just cancel each other out perfectly.
Right. So the expected value of a single toss, E of R sub I, is strictly 0.
Okay, that makes total sense. But then the text immediately pushes us to look at a slightly different metric. And this ends up being like the secret engine to everything we will discuss today.
Oh, this is the big one.
It asks us to consider the expected value of the square of that toss. So the expected value of R sub I squared.
Right, and consider the mechanics of squaring those outcomes. It's so important. If you flip heads, your outcome is +1. 1 squared is 1.
Sure.
But if you flip tails, your outcome is -1. And -1 multiplied by -1 is
Also positive.
exactly. Regardless of the outcome of the flip, the squared result is always 1. Therefore, the expected value of the squared toss is simply 1.
Because there's no negative option anymore. It's always +1.
Right.
And what if we compare two completely different tosses? Like, say we multiply the outcome of the second toss by the outcome of the fifth toss.
Yeah.
The text represents this as R sub I times R sub j.
Well, assuming I and j are different tosses, the expected value of their product is 0.
Wait, why is it 0?
Because the second toss has absolutely no impact on the fifth toss. They are completely statistically independent.
Oh, right. The coin doesn't care what happened 3 tosses ago.
Exactly. When you multiply two independent random variables that both have an expected value of 0, their product also has an expected value of 0.
Okay, so we understand the individual flips.
Yeah.
But a gambler sitting at a table doesn't just care about isolated flips, right?
Yeah.
They care about their wallet. They care about their cumulative winnings.
Yeah, the running total.
Exactly. So the text uses the variable S sub I to denote the total cumulative amount of money you hold up to and including the IFIC toss.
So you walk up to the table with empty pockets, meaning S sub 0 equals 0.
Right.
From there, S sub I is simply the running sum of all your individual R tosses.
And this is where we run into this concept called conditional expectation, which the notes say is vital for understanding financial markets.
It's critical.
Yeah.
We really need to distinguish between what you expect before the game starts and what you expect while you are actually in the thick of it.
Okay, break that down for me.
So, if we evaluate our expectations before you even sit down at the table, your expected total winnings at any future toss I written as E of S sub I is just 0.
Because the game is fair.
Exactly. You have no structural advantage. Over time, before you even start, you expect to make nothing.
Right. But I want to pause here and make sure I'm fully wrapping my head around this. Because expectation changes the moment the coin is actually in the air, right?
Yes. Let's put you in the game. Imagine you've made 5 tosses.
Okay.
And let's say you had a really lucky streak early on, and you are currently sitting on $5 of pure profit. The coin is in your hand for the 6th toss. What is your expectation for your total wealth after this upcoming flip?
Well, the game is still fair, right? So the next flip on its own has an expected value of 0.
Right.
So my best guess for my total wealth after the 6th flip isn't 0 anymore. It's the $5 I already have plus the $0 I expect to make on the next flip. So my expectation is just $5.
Boom. You have just defined conditional expectation.
Oh, awesome.
Yeah, the expectation of your wealth after the 6th toss, conditional upon the known results of the first 5 tosses, is simply your current wealth. Your best guess for the future is entirely anchored to your present state.
And the lecture notes actually give a formal name to this phenomenon. They call it the Markov property.
Ah, yes. The Markov property.
The technical definition they provide is that the distribution of the value of the random variable S sub I, conditional upon all of the past events, depends exclusively on the immediately preceding value, S sub I minus 1.
Right. And a process that possesses the Markov property is often described as memoryless.
Memoryless, I like that.
Yeah, the coin does not remember that you just flipped 5 heads in a row. The probability of flipping heads on the next toss remains exactly 50%.
So the history of how you accumulated your $5, like whether it was a slow, agonizing grind of wins and losses or just an immediate hot winning streak, that's completely irrelevant to the probability of your next step.
Completely irrelevant.
You know, I think of the Markov property like, imagine being blindfolded and dropped from a helicopter into the middle of a massive, complex labyrinth.
Okay, I'm with you.
When you finally take the blindfold off, you're standing at a specific intersection in the maze. It absolutely does not matter what series of left and right turns the helicopter pilot took to lower you into that exact spot.
Right, the path there doesn't matter.
Exactly. Your options for moving forward, turning left, turning right or walking straight, are dictated purely by the geometry of the intersection you are standing in right now. The future possibilities are defined entirely by your present location, not by the historical path you took to arrive there.
That analogy perfectly captures the essence of a memoryless system. That's exactly how it works. And it serves as the foundation for the second major property outlined in the text, the martingale property.
Right, the martingale property. The notes state that the conditional expectation of your winnings at any future time is simply the exact amount you currently hold.
Which is just a formal way of stating what we just figured out with the $5.
Right. The math notation they use is E of S sub I given S sub j, where j is sometime in the past, before I equals S sub j.
And the martingale property is essentially the mathematical translation of a fair game.
Okay, how does that apply to finance, though?
Well, in the context of quantitative finance, assuming a market is perfectly efficient, a stock price modeled as a martingale implies that the absolute best predictor of tomorrow's closing price is simply today's closing price.
Wow, really?
Yeah. You are not expecting the asset to systematically drift upward or downward. Any future movement is pure, unadulterated noise. Your expected future wealth is locked to your current wealth.
But wait, hold on. Even if my mathematically expected wealth doesn't change, my actual tangible wealth is bouncing around wildly while I play.
Oh.
I mean, I'm winning dollars, I'm losing dollars. The emotional experience is chaotic.
Oh, absolutely. It's a roller coaster.
And I think that brings us to the third big concept from this coin toss section, quadratic variation.
Yes, quadratic variation. And this specific concept is going to become the central engine for all the calculus we explore later. It is huge.
Okay, so what is it?
The quadratic variation of a random walk measures the accumulated volatility. You calculate it by looking at the change in your wealth from one single step to the next, which is S sub j minus S sub j minus 1, squaring that specific change, and then adding all of those squared changes together over the entire duration of the game.
Let me push back on this for a second because it feels like an unnecessary mathematical complication.
Okay, push back.
If I want to know what happened during the game, why wouldn't I just add up my normal changes? Why do we care about squaring them? Like if I just sum up my wins and losses, I get my final wealth. What does squaring the changes tell us that a simple sum completely misses?
Okay, think about the sequence we discussed at the very beginning. Remember, you went up, down, and finished exactly at 0.
Right, I broke even.
Right. Now, if you just add up your raw changes, plus 1 minus 1 plus 1 minus 1, they perfectly cancel each other out. The sum is 0. If a mathematician only looked at your simple sum, they would look at that 0 and conclude that absolutely nothing happened. But you sat at the table. You experienced the game. Something did happen.
Yeah, I experienced the stress of the swings.
Precisely. You experienced volatility. Squaring the changes strips away the directional vector, the positive or negative sign, and leaves you with the pure magnitude of the movement.
Oh, because squaring a negative makes it positive.
Exactly. It measures the total energy expended during the path you took. Think of it like the odometer on a car versus a GPS displacement measurement.
Oh, I like that.
Right. If you drive 10 miles north and then 10 miles south, your total displacement from your starting point is 0. You're back where you started.
Mm-hmm.
But your odometer read 20 miles.
It tracked all the effort.
Yes. Squaring the changes is how mathematicians build an odometer for a random walk.
Okay, that makes so much sense. So, because every individual step in our coin game is a change of either +1 or -1, when you square it, the result is always exactly +1. So if you toss the coin I times, you are simply adding the number 1 to your running total.
Yeah.
I times, which means the total quadratic variation over I tosses is mathematically guaranteed to equal I.
Exactly. It acts as a flawless counter for how much action or volatility has occurred, completely independent of whether the player is currently winning or losing the game. The total variance of your wealth grows in strict, direct proportion to the number of steps you take in the random walk.
See, that structural reality makes perfect sense for a game involving a physical coin. It's a discrete, clunky, step-by-step process. You flip, the coin lands, you tally the result, you prepare for the next flip.
Very slow, very discrete.
Right. But if we're trying to model real global financial markets, this step-by-step framework is woefully inadequate. The market doesn't wait for a referee to flip a coin.
No, it certainly doesn't.
Electronic exchanges move constantly, smoothly, continuously. Asset prices update every microsecond. If we want our mathematical model to reflect financial reality, we have to dramatically speed up our game.
We have to push this discrete random walk to its absolute theoretical limit. We have to leave the world of discrete steps and enter continuous time.
Which transitions us directly into the second major phase of the lecture notes, speeding up time and the birth of Brownian motion.
This is where things get really wild.
Yeah. So to model a continuous market, the text instructs us to change the fundamental rules of our coin tossing experiment. First, we restrict the entire allowed duration of the game to a specific finite time period. Let's call that total time period T.
Okay, so imagine it's 1 minute. If we decide to perform our original sequence of 6 tosses within that 1 minute, each individual toss takes a specific fraction of that time. Specifically, it takes t divided by 6, or 10 seconds per toss.
Okay, 10 seconds a toss. But the notes dictate that as we change the time, we must also dynamically change the size of the bet.
This is crucial.
We are no longer wagering a flat $1. The size of the bet is mathematically scaled to the square root of the time fraction. So the bet becomes the square root of t divided by 6.
And this scaling mechanism is where the true mathematical magic occurs. Our ultimate goal is to speed the game up to an infinite frequency. We want to execute n total tosses within our fixed time t. And we are going to push the value of n toward infinity. Millions, billions of tosses packed into our single minute.
Wow, okay, so the physical time between each toss shrinks down to almost nothing. The time step for a single microtoss is 2 divided by n.
Right. And crucially, the bet size, the physical amount of wealth we win or lose on each tiny rapid-fire toss, is strictly defined as the square root of t divided by n.
Okay, here is where I really need to pause, because my intuition is completely breaking down here.
It's totally fine. It's a huge conceptual leap.
If we are shrinking the time interval by dividing it by n, why wouldn't we just shrink the bet size symmetrically by dividing it by n as well? Like, why introduce this complex square root scaling? It seems totally arbitrary.
It's actually the furthest thing from arbitrary. This is the most critical decision in stochastic modeling. It comes down to maintaining a functional, measurable reality. The text emphasizes this under a property it calls finiteness.
Finiteness, okay.
The author explicitly states that these new scalings have been chosen very carefully for a specific reason. Look at the rates of change. The time step is decreasing proportionally to n to the power of -1, which is just dividing by n.
Right.
But the bet size is decreasing proportionally to n to the power of -1/2, which is taking the square root.
Okay, meaning the size of the bet is shrinking much, much slower than the size of the time step is shrinking.
Exactly. And we can prove why this asymmetry is literally mandatory by looking at the alternatives. Imagine what would happen if we scaled the bet linearly, exactly the same way we scaled time.
Okay, let's run that scenario.
Suppose we divide the time head by 1 million to get 1,000,000 tiny steps. Symmetrically, we divide our $1 bet by 1,000,000. You are now taking 1,000,000 tiny steps, but each step only moves your wealth by 1/1,000,000th of a dollar.
Right.
The absolute maximum you could possibly move if you won every single toss is $1. But this is a random walk. You are taking steps forward and backward. The law of large numbers dictates that over 1,000,000 tosses, the positive and negative microsteps will cancel each other out with extreme efficiency.
Because you're flipping so fast, the wins and losses just blend together.
Exactly. Your total movement over time, too, will flatline. The mathematical limit of that process is just a flat deadline at 0. There is no volatility at all.
Okay, so symmetrical scaling kills the noise completely,
Yeah.
makes the model completely useless.
Yes.
What if we go the other way then? What if we don't shrink the bet size enough? Like, what if we kept the bet locked at a solid $1, but still squeezed 1,000,000 random tosses into our 1-minute time frame T?
Well, that results in the opposite catastrophe. The volatility physically explodes. You would be experiencing $1,000,000 worth of wild upward and downward fluctuation inside a single minute. The variance goes to infinity.
Yeah.
The random walk would immediately shoot off the chart to positive or negative infinity. It would be utterly useless for modeling a stock price. The only mathematical path to generate a process that doesn't instantly flatline into a dead pulse and doesn't instantly explode into infinite chaos, a process that stays finite, stable, and measurable, is if the increment size scales precisely with the square root of the time step.
It's like a Goldilocks scaling factor.
That's a great way to put it.
It's the exact razor-thin mathematical sweet spot that allows chaos to exist continuously without destroying the model. And the notes confirm that as n approaches infinity, this extremely fast, perfectly square root scaled random walk transforms into a continuous mathematical object. It actually earns a new title. It becomes Brownian motion, which the text denotes mathematically as x of t.
And because we carefully, deliberately built this continuous object out of our discrete coin toss game, it inherits all of those foundational properties we just discussed. They are just adapted for a continuous reality.
Let's walk through how those four properties translate, because they really are the architectural pillars of everything quantitative analysts do.
Let's do it.
The first is continuity. The paths of Brownian motion are continuous. There are no microscopic gaps, no discontinuities, and no teleporting from one value to another. It traces an unbroken line.
Perfect. The second is that it retains the Markov property. The conditional distribution of the future path of the Brownian motion depends solely on its exact coordinate right now. It retains no memory of the jagged path it took to arrive at that coordinate.
Memoryless maze. Got it. Third, it remains a martingale. Your most statistically accurate prediction for its value at any point in the future is simply its current present value.
Right. And the fourth property is perhaps the most profound: quadratic variation.
Our odometer.
Exactly. Remember how in our discrete coin toss over I steps, the total quadratic variation was exactly equal to I?
Yeah, number of steps equal total variation.
Well, in our continuous model, over a total time period t, if we chop that time up into infinitely small microscopic segments, square the change during each tiny segment, and sum all those square changes together, the total quadratic variation perfectly equals t. The accumulated volatility over the path is exactly equal to the physical time that has elapsed.
That is wild.
Yeah.
Time and volatility become perfectly linked.
They do. And finally, the notes detail the property of normality. Because our continuous line is essentially the sum of millions of tiny, independent, rapidly occurring coin tosses, the central limit theorem dictates the shape of the outcomes.
Right. Statistics 101.
Yeah, over any finite increment of time, the total change in the Brownian motion is normally distributed. It forms a perfect symmetrical bell curve with a mean centered exactly at zero and a variance that is exactly equal to the length of the time step.
Which logically implies that the standard deviation, the measure of the average size of the asset swing away from the mean, is the square root of the time step.
Exactly. And understanding this brings us to a visual reality that is incredibly striking.
Visualizing this math is honestly my favorite part of the theory. If you look at a computer-generated graph of pure Brownian motion, it looks completely indistinguishable from a jagged, chaotic, real-world stock chart.
You literally couldn't tell them apart.
But because the underlying math is driven entirely by that square root scaling, the graph possesses a shocking fractal property. Imagine you take a stock chart spanning an entire year, and it looks like a jagged mountain range. Right? Yeah. If you zoom in on just one single month of that chart, you would expect it to smooth out. Like closer up, things should look flatter. But it doesn't. It looks exactly as jagged as the one-year chart.
Its jaggedness is infinite.
It is. If you zoom in further to one single day, it is still violently jagged. 1 minute. Still infinitely jagged. No matter how deeply you magnify the line, you will never ever find a smooth, straight segment. The unpredictable randomness is woven into the very fabric of the math at every conceivable microscopic scale.
And that infinite, unbreakable visual jaggedness is captured in a very specific, vital piece of notation introduced in the text. Whenever we need to talk about an infinitesimally small microscopic change in this Brownian motion, we write it as dx.
dx, got it.
The symbol dx represents a tiny random increment. It is a normal random variable with a mean of 0 and a standard deviation equal to the square root of our tiny time step, which we call dt.
Okay, so we have successfully built a continuous mathematical line, x of t, that perfectly simulates random market movement without exploding or flatlining. We have practically captured lightning in a bottle.
We have.
But if a quant actually wants to use this Brownian motion to model a complex stock portfolio or to calculate the fair price of an options contract, they cannot just stare at the line on a screen.
No, they have to put it to work.
Right. They have to perform operations on it. They have to put it into equations and calculate its rate of change. And here is where we hit a massive paradigm-shifting roadblock.
We hit the exact coordinate where standard classical mathematics completely and utterly breaks down.
And this brings us to part 3 of our deep dive, the collision of calculus and chaos. The lecture notes lay out the dilemma with stark clarity. In the real world of finance, we almost never care exclusively about the raw underlying Brownian motion x of t. We usually need to analyze a function of that random variable.
Right. For instance, reliable. But alongside it, we have our Brownian motion, x, which is bouncing around violently and randomly.
In ordinary calculus, if we want to see how our function f changes, we write a differential equation. We are deeply accustomed to the calculus developed by Isaac Newton and Gottfried Leibniz, where the entire mechanical premise relies on taking limits as the microscopic change in time, dt, shrinks closer and closer to zero.
Right. You isolate an unimaginably tiny slice of time, and you measure how much your function changed within that specific tiny slice.
And that concept is the bedrock of physics and engineering. Standard calculus operates on the fundamental assumption that if you zoom in close enough on any curve, no matter how complex, it eventually smooths out and looks like a straight line.
It assumes that if your time step dt is incredibly small, the corresponding change in your variable is also incredibly small, and the relationship is stable and predictable.
But the text reveals that when we attempt to apply this logic to Brownian motion, we strike a fatal mathematical flaw. And the root cause of this flaw leads directly back to the Goldilocks scaling we instituted to build the model.
It always comes back to the scaling.
It does. Remember, our tiny random increment, dx, is inherently scaled by the square root of our tiny time step dt.
Which creates what we can call the magnitude problem. Dx is strictly proportional to the square root of dt, and human intuition severely fails us when we start dealing with infinitesimally small fractions. When you are operating close to zero, a square root is vastly, overwhelmingly larger than the number itself.
Okay, let me stop right here to make sure this is crystal clear because it's wildly counterintuitive.
Right.
We spend our lives dealing with whole numbers, right?
Right.
The square root of 100 is 10. The square root of 25 is 5. We are deeply conditioned to believe that taking a square root makes a number smaller.
It shrinks it.
Yeah, but you are saying that when dt is a microscopic decimal, the square root is actually bigger.
It is bigger by orders of magnitude. Let's walk through the decimal logic slowly.
Okay, let's do it.
Imagine our time step. dt is 1/100th of a second. So dt equals 0.01.
Okay, dt is 0.01. If I want the square root of that, the square root of 0.01 is 0.1, which is 1/10.
Precisely. The value 0.1 is exactly 10 times larger than 0.01. The square root is 10 times bigger than the original number.
Oh, wow, okay.
Let's zoom in further. What if we shrink our time step dt to 1/10,000th of a second? So dt is 0.0001. The square root of 0.0001 is 0.01.
Look at the sheer scale of the divergence now. The square root is now a full 100 times larger than the underlying time step.
Yes. So as dt shrinks closer and closer to absolute zero, which is exactly what we are required to do when taking a limit in calculus dx is not shrinking alongside it at the same speed. It is utterly dwarfing dt.
So on a microscopic scale, the chaotic random change, dx, is orders of magnitude more massive than the deterministic time step dt.
Exactly. Now, in standard Newtonian calculus, if you take a microscopic change in a variable, say dx, and you square it to get dx squared, the resulting number is so unbelievably infinitesimal that mathematicians universally agree to just ignore it. They sweep it under the rug, it rounds to zero, and has no impact on the final equation.
Makes sense.
But look at what happens in our stochastic universe. If you take our massive random change, dx, and you square it, what is the result of dx squared?
Let me think. Because dx is fundamentally scaled by the square root of dt, if you square it, the square root simply cancels out.
Yeah.
The value of dx squared becomes directly proportional to exactly dt.
Boom. And you cannot sweep dt under the rug.
No.
dt is the foundational metric of the equation. It is a first-order component. The mathematical reality is that the random noise embedded in Brownian motion is so incredibly aggressive and so disproportionately large at the microscopic level that squaring it produces a real, tangible, measurable physical effect that standard calculus is completely blind to.
So the rules laid down by Isaac Newton simply do not function in this landscape.
They fail completely.
If a quantitative analyst tries to use high school calculus to determine the derivative of a stock market model, they will calculate the wrong trajectory, misprice the asset, and lose billions of dollars for their fund. We cannot use the old tools. We require an entirely new mathematical toolkit specifically designed to calculate derivatives in the presence of overwhelming randomness.
We require the genius of Kiyoshi Ito.
Which brings us to the centerpiece of the lecture notes, part 4. Ito's lemma, the rule of thumb that changes everything. Kiyoshi Ito was a brilliant Japanese mathematician who recognized this magnitude problem and developed the framework to solve it.
Yeah, the notes detail how Ito's framework forces us to abandon ordinary differential equations entirely and work exclusively with stochastic differential equations, or SDEs.
Okay, what do those look like?
The general architecture of an SDE is that the total change in our function, df, must be equal to some deterministic components multiplied by dt, plus some random components multiplied by dx.
But how do we find those components if standard derivatives don't work? The text suggests a really fascinating approach. We are going to temporarily throw caution to the wind.
Right.
We're going to start by constructing a naive Taylor series expansion of our function f, deliberately ignoring the chaotic nature of x, just for a moment to see what happens.
Right. And a Taylor series is a fundamental tool in mathematics used to approximate the value of a complex function by adding up an infinite sequence of its derivatives.
Okay.
If we want to predict the new value of our function f after taking a tiny random step forward, so we are trying to find f of x plus dxa, standard first-order Taylor expansion tells us it should equal our current known value, f of x, plus the first derivative of f with respect to x multiplied by the size of the step, dx.
But the beauty of a Taylor series is that it doesn't stop at the first derivative, right? It contains an infinite chain of increasingly microscopic terms to refine the approximation.
Yes.
The very next term in the series is plus 1/2, multiplied by the second derivative of f with respect to x, multiplied by the step size squared, dx squared.
And here we reach the crux of the issue. As we proved just moments ago in ordinary calculus, that dx squared term would be infinitesimally small, and Newton would tell us to cross it out and ignore it.
Right, sweep it under the rug.
But the critical adjustment dictated by Ito's world, according to the notes, is that because of the unique square root scaling we use to construct Brownian motion, because of that quadratic variation we traced all the way back to the total energy of the coin toss, the dx squared term is definitively not tiny.
We cannot ignore it.
We cannot. And even more shockingly, as we evaluate it at the microscopic limit, it ceases to be truly random.
Wait, what? It stops being random.
This realization is the profound philosophical breakthrough of the entire lecture. Consider the raw variable dx. It is pure, unfiltered noise. It is completely unpredictable. It could spike positive or it could plunge negative. But look at dx squared. Because any number multiplied by itself becomes positive, the squared term is uniformly positive. And as we shrink our time steps smaller and smaller toward the calculus limit, the wild, chaotic variations of that squared randomness begin to perfectly converge onto their statistical average.
Oh, wow. And as we established, when we looked at the variance of the normal distribution of our increments, the exact average, the expected value of that squared randomness, is simply the time step itself. It is exactly dt.
Therefore, the rule of thumb that Ito introduces, the rule that literally rewrites the laws of calculus for finance, is shockingly simple to write down on a chalkboard. Dx squared equals dt.
I want to let the philosophical weight of that sink in. You take pure, unadulterated chaos, you square it, and it miraculously transforms into a perfectly predictable, deterministic ticking clock.
It acts as the ultimate mathematical bridge connecting pure unpredictability with absolute certainty. So, returning to our Taylor series expansion, Ito tells us we are strictly forbidden from crossing out that second derivative term. We must keep it. But we use our rule of thumb to replace the chaotic dx squared symbol with the deterministic dt symbol.
To make this concrete, let's actually execute the math on the simple function the text uses. F of x equals x squared. Let's find its true stochastic derivative, df.
Okay, the process starts normally. We calculate the standard derivatives. What is the first ordinary derivative of x squared?
That's basic high school calculus. The exponent 2 drops down to the front, leaving us with 2x.
Next, we need the second ordinary derivative. So we take the derivative of our result, 2x.
The x variable drops away, leaving us with just the constant number 2.
Now we assemble the pieces using Ito's modified formula. The total change in our function, df, equals the first derivative, which is 2x multiplied by dx, plus the mandatory Ito correction term, 1/2 multiplied by the second derivative, which is 2 multiplied by dx squared.
Okay, let's simplify that equation. The 1/2 multiplied by the 2 cancels out to simply 1. And Ito's crucial rule of thumb commands us to swap out the dx squared for dt. So that entire complex second term gracefully collapses into 1 multiplied by dt, or simply dt.
Which gives us our final, rigorously correct stochastic differential equation. df equals dt plus 2x dx.
Look at the profound difference here. If you presented the function x squared to a brilliant engineer trained only in Newtonian calculus and asked for the derivative, they would confidently write down 2x dx.
Right.
But Ito intercedes and says, your math is blind to the chaos. The true answer is 2x dx plus this seemingly magical extra dt term floating at the front.
And that isolated plus dt term is the literal mathematical footprint left behind by the chaos. It represents the physical cost of the volatility. It is the direct consequence of the immense quadratic variation we observed building up in the coin toss. Because the underlying random path of the Brownian motion is so incredibly jagged, the mathematical function of that path actually accumulates value and grows slightly faster than standard, smooth calculus would ever predict.
It is staggering. It is like discovering a hidden physical force, a secret tax embedded in the laws of probability.
That's a beautiful way to phrase it.
Now that we understand the absolute necessity of these new rules for taking derivatives of random variables, how do quantitative analysts put them to work? How do they use SDEs to build functional models of a reality as complex as the stock market?
Well, that structural application brings us to part 5, building financial models with stochastic differential equations.
SDEs are the fundamental architecture of quantitative finance, right? They are the primary tools used to model any random quantity evolving over time. The notes use the most universal example, modeling a stock price, which they denote with a capital S.
The foundational philosophy of an SDE is beautifully intuitive. It asserts that the total microscopic change in the stock price over a tiny fraction of time, which we call DS, is constructed by adding together two fundamentally distinct components, a strictly deterministic component and a purely random component.
The formal mathematical structure provided in the text reads, ds equals f of s and t dt plus g of s and t dx. Let's dissect the meaning behind those two halves.
We begin with the first term, f of s and t multiplied by dt. This represents the deterministic half of the equation. In quantitative terminology, this is defined as the growth rate, or the drift.
The drift is the underlying trajectory. It's what you expect the asset's value to do on average if you possessed a magic wand and could completely eliminate all market noise, all breaking news, and all irrational panic. It is the core trend, which is why it is mathematically attached to dt, the relentless, predictable forward march of time.
Then we have the second term, g of s and t multiplied by dx. This represents the random half of the equation. The notes identify this as the volatility of the asset S.
This is the chaos engine. This term captures the unpredictability, the sudden earning shocks, the geopolitical crises, the algorithmic flash crashes. It is entirely driven by dx, our jagged, square root scaled Brownian motion. To visualize how these two competing forces interact to create a single stock price, I like to use the analogy of a person walking a dog on a very long leash across a wide open park.
Let's explore the mechanics of that metaphor. It's really helpful.
The human walking across the park represents the drift. The person has a clear destination, perhaps the park exit. They are moving forward at a steady, intentional, predictable pace. If you only look at the human, you are looking at the dt term.
Right.
But the dog on the end of the leash represents the volatility. The dog has no fixed destination. It is erratically darting 10 feet to the left to sniff a tree, suddenly sprinting 20 feet to the right to chase a squirrel, lagging behind and then bolting forward. The dog's erratic movement is the dx term.
And it is crucial to recognize that the actual stock price, S, is neither the person nor the dog in isolation. The stock price is the exact chaotic path traced into the grass by the dog's paws. It is the constant mathematical synthesis of the forward deterministic momentum of the human walker, forcefully combined with the wild, unpredictable bouncing of the dog.
And the true power of mathematical finance, the reason quants are paid millions of dollars, is that by carefully tweaking the mathematical parameters describing the human, the drift equation, and the dog, the volatility equation, you can simulate entirely different financial universes. You can build bespoke realities to match different types of real-world assets.
And the lecture notes dedicate a significant section to demonstrating this power, providing 4 highly specific flavors of these financial realities to illustrate how seemingly minor tweaks to the SDE alter the fundamental physics of the model.
Let's deeply explore these variations in Part 6, 4 flavors of financial reality. We're going to walk through these 4 models and analyze the profound economic implications of changing a single mathematical symbol.
We will begin with the most basic construct. Example 1, a simple Brownian motion with drift. The equation is presented as ds equals mu dt plus sigma dx.
Let's translate the Greek. Here, mu is simply a constant static number representing a steady, unchanging growth rate, and sigma is also a constant static number representing a fixed level of noise or volatility.
So, in this specific universe, the human walks at an exactly constant speed, and the dog darts around with exactly the same amount of energy forever. What does the resulting path of the stock look like?
Well, the notes include a visual graph of a simulation run with this equation, and the author makes a very dry yet economically devastating observation. In this realization, S has gone negative.
Which exposes a catastrophic structural flaw in the model if applied improperly.
Absolutely. Think about the economic reality. If the dog's volatility is a constant fixed amount, say $10 of random movement, and the stock price starts at $15, a string of bad luck will inevitably drag the price down to $5 and then eventually down to negative $5.
Right.
But S is meant to represent a real-world equity stock. A corporate stock price physically cannot drop below zero due to limited liability. If a company goes bankrupt, the stock is worth zero, not negative $10. You cannot owe money simply for holding a share. Therefore, this simple constant model is fundamentally broken for modeling equities.
Recognizing this flaw forces us to adapt the model to respect reality. This evolution leads us to example 2. The mathematicians alter the equation to read ds equals mu s dt plus sigma s dx.
Notice the critical addition there. Both the drift term and the random volatility term are no longer isolated constants. They are now multiplied by S, the current price of the stock itself.
Analyzing the implications of that single added variable reveals a brilliant mathematical solution to the negative price problem. Consider the mechanics of the random noise term, sigma s dx, as the stock price S suffers heavy losses and drops closer and closer to zero.
Because the total volume of the noise is directly multiplied by S, as S shrinks down to a tiny fraction of a dollar, the volume of the noise shrinks alongside it.
Precisely. The increments, the maximum size of the random steps the asset can take, become microscopically small as the asset loses value. It is as if the stock price is approaching an impenetrable concrete wall at zero, and the closer it gets to the wall, the shorter its steps are forced to become. The text explicitly confirms the result of this modification. If S starts out positive, it can never go negative. It mathematically, physically cannot cross the zero barrier.
Economically, this makes profound sense because it shifts the model from calculating absolute dollar changes to calculating percentage changes. In reality, a 10% drop on a massive $100 stock is a $10 move, but a 10% drop on a struggling $1 stock is only a 10-cent move. The absolute volatility scales down proportionally with the price. This specific proportional SDE is not just a theoretical exercise. It is the fundamental mathematical assumption underpinning the Black-Scholes options pricing formula, which literally built the modern derivatives market.
It is massive. However, equities are only one facet of the global financial system. Quants also need to model the behavior of debt, specifically interest rates. And interest rates behave according to entirely different economic forces, which requires us to construct a completely different reality. This brings us to example 3, the mean reverting or Vasicek model. The SDE undergoes a major structural shift. ds equals parenthesis nu minus mo s, close parenthesis dt, plus sigma dx.
Let's look at the volatility term first. The S is gone. We're back to just the constant sigma dx. The noise is static again. But the drift term has been entirely rewritten into this complex bracketed structure, nu minus mu s, all times dt.
We need to unpack the internal mechanics of that specific drift term. It is engineered to act as a mathematical rubber band. Let's run a thought experiment. Suppose our variable S experiences a massive upward shock and becomes an exceptionally large positive number. Look at the term minus mu S. Because S is massive, multiplying it by negative mu creates a massive negative number. This large negative number completely overwhelms the constant positive nu value inside the bracket.
So the total sum inside the drift bracket becomes negative. This means the deterministic walker is now actively walking backward. The model is purposefully generating downward pressure to push the asset's value lower.
Exactly. Now reverse the scenario. If S collapses and becomes a very small number or drops into negative territory, that minus mo S term actually flips the math and creates a powerful positive drift. It actively pulls the value back up. Regardless of where the asset wanders, the drift term is constantly stretching and pulling it back toward a central long-term average value or mean.
The lecture notes point out that if we change the variable symbol from a stock's S to an R, this exact equation becomes the famous Vasicek model, used extensively to map the trajectory of short-term interest rates. And aligning this with macroeconomic theory makes perfect sense. We do not expect national interest rates to experience exponential, unbounded growth to infinity like a wildly successful tech stock. Interest rates are artificially managed by central banks, like the Federal Reserve. If rates spike too high, the economy chokes, and the central bank is forced to cut them. If rates drop too low, inflation runs hot, and the bank is forced to raise them. They naturally hover around a long-term historical average. They revert to the mean.
It is a beautiful alignment of mathematical structure and macroeconomic theory. However, if we scrutinize the equation closely, we uncover a lingering vulnerability.
There is always a vulnerability. The flaw lies in the volatility term. Because it is defined simply as the constant sigma dx, the random noise is completely blind to the asset's current price. It doesn't care if the interest rate is at 10% or 1%, the dog has the exact same amount of erratic energy, which means a severe random shock can easily overpower the rubber band and push this interest rate model across the zero line and into deep negative territory. Now, while we know that slight negative interest rates have occasionally occurred in real-world European and Japanese markets, historically, classical economists demanded models that absolutely prevented them.
Which necessitates one final masterful refinement presented in the text. Example 4, the Cox, Ingersoll, and Ross model, universally recognized on Wall Street as the CIR model.
The SDE for the CIR model represents the pinnacle of this modeling logic. ds equals parenthesis nu minus mu s close parenthesis dt plus sigma s to the power of 1/2 dx.
This equation brilliantly merges the most effective components of the previous realities. It retains the bracketed mean-reverting rubber band drift from the Vasicek model, ensuring the rates don't spiral to infinity. But it fundamentally alters the random volatility term. It introduces a scaling factor, but instead of scaling linearly by s, it scales by the square root of s, written algebraically as s to the 1/2.
And that single elegant modification solves the Vasicek problem entirely. If the modeled interest rate suffers a shock and drops dangerously close to zero, the square root of s also approaches zero. This forces the total magnitude of the random volatility to mathematically decay to zero. The erratic noise is physically stripped of the energy required to push the rate across the barrier into negative territory. It creates an absolute impenetrable floor at zero, while simultaneously maintaining the mean reverting pull to a long-term average.
Examining these 4 models back-to-back serves as a masterclass in the art of quantitative modeling. It demonstrates exactly how analysts sculpt bespoke mathematical realities, dictating the physical boundaries of a virtual universe simply by making microscopic adjustments to the deterministic drift and the random volatility parameters.
It is incredible. Swapping a linear s for a square root of s literally rewrites the fundamental laws of physics for that specific financial instrument.
Yet, despite the elegance of these SDEs, the lecture notes are rigorous. They cater to mathematical purists. Throughout this discussion, we have heavily relied on Ito's rule of thumb, dx squared equals dt. We have treated it as a magical axiom that bridges chaos and certainty. But the text refuses to let us simply trust the magic. It demands we peek under the mathematical hood one final time to understand how these SDEs are rigorously, formally defined, and to actually prove, without a shadow of a doubt, that our rule of sum is mathematically ironclad.
It is time to brace ourselves. We are entering part 7. Under the hood integrals and mean square limits. The text begins by dropping a bit of a bombshell. Writing out equations in the format df equals dt plus dx is technically just a convenient shorthand. True SDEs are formally defined not as differentials, but as stochastic integrals.
Conceptually, an integral is simply a mathematical tool used to calculate the total accumulation of a continuously changing quantity by summing up an infinite number of infinitesimally small slices. The text presents the true, rigorous form of an SDE as w of t equals the integral from time 0 to time t of the deterministic drift components, plus the integral from time 0 to time t of the purely random components attached to dx.
The challenge the text addresses is how to make that second integral, the one summing up infinite slices of pure randomness, mathematically valid. To construct the formal proof explaining exactly why dx squared perfectly equals dt, the author introduces a demanding analytical concept known as the mean square limit.
I want to guide our exploration of this concept carefully, as it represents the heavy, foundational machinery of quantitative finance. We are going to conceptualize the mechanics of the proof without getting lost in the raw algebra. Our ultimate objective is to undeniably prove that if you sum up all the microscopic squared random changes over a period, the total perfectly equals the physical time that has passed.
To structure this proof, the text constructs an expectation formula. It is essentially setting up a stress test. It calculates the difference between the massive sum of all the squared random changes and the simple time variable t. If Ito's rule of thumb is a true law of nature, those two values should be identical. meaning the difference between them must be exactly zero.
To conduct the stress test, we look at the expected value of that difference, but crucially, we square the entire difference. By squaring the difference, we guarantee that we are measuring the absolute positive magnitude of any potential error. We are hunting for any discrepancy, positive or negative.
The notes proceed to expand this massive squared equation. Conceptually, it is identical to expanding a binomial algebra problem, like parenthesis a minus b, close parenthesis squared, which expands into a squared minus 2ab plus b squared.
Let's look at the implications of that first expanded term, a squared. This term requires us to take the sum of our squared random changes and square it again. This means we are effectively taking our tiny random increments and raising them to the fourth power.
Raising pure randomness to the fourth power sounds like a calculation that would spiral completely out of control.
It would if we didn't understand the underlying architecture of our model. But remember the properties we locked in when we built Brownian motion. We established that these tiny increments are normally distributed. They form a perfect bell curve with a mean of 0 and a highly specific variance equal to t divided by n.
Right, and the text confirms that the expected value of the increment squared is equivalent to its variance, which is exactly 2 divided by n.
But calculating the expected value of the increment raised to the fourth power requires a deeper statistical tool. Fortunately, the properties of a normal distribution provide a direct shortcut. The expected value of any normally distributed random variable raised to the fourth power is mathematically guaranteed to be exactly 3 times its variance squared.
So if our variance is t divided by n, squaring that gives us t squared divided by n squared. Multiplying by the constant 3 yields 3 squared divided by n squared.
Exactly. The text meticulously substitutes these calculated expected values back into the massive expanded algebraic equation. It calculates the sum of the fourth powers, it calculates the complex cross terms generated by the expansion, and it calculates the minus 2ab interaction terms.
And this is where the sheer beauty of the mathematics reveals itself. When the author simplifies that intimidating, sprawling algebraic mess, a profound cancellation occurs. All of the terms containing t squared perfectly mathematically annihilate each other. After the dust settles, the only thing remaining of our massive error calculation is an equation whose value is proportional to 1 divided by n. The text writes this formally as order of 1 over n, or O of 1 over n.
Which brings us to the ultimate grand conclusion of the rigorous proof. We built our continuous Brownian motion by pushing n the total number of tiny time steps toward infinity. What happens to our remaining error term, 1 over n, as n becomes infinitely large?
As the denominator n scales toward infinity, the value of the fraction 1 over n shrinks relentlessly until it hits absolute 0. The entire expected error of the equation completely vanishes.
Therefore, in the rigorous mean square limit sense, the difference between the sum of the squared random changes and the time t is provably 0. They are perfectly equal. This provides the concrete, unassailable mathematical proof that the integral of dx squared strictly equals t. It is the absolute formal validation of Ito's magical rule of thumb.
What I find so deeply fascinating about tracing this proof conceptually is what it implies about the nature of reality. The math definitively proves that chaos actually has a speed limit. When you take millions of microscopic, completely unpredictable, violently erratic zigzags, square them to capture their raw energy and add them all together, the wild randomness doesn't compound into infinite noise. Instead, it perfectly cancels itself out, stripping away the unpredictability and leaving you with nothing but the steady, deterministic, reliable march of a ticking clock. It is literal poetry, written in the language of algebra.
It truly is a masterpiece of logical construction. Over the course of this deep dive, we have watched the architects of quantitative finance build an incredibly robust, incredibly powerful framework.
Let's summarize the immense journey we have taken through these lecture notes. We began with the simplest, most mundane concept imaginable, tossing a coin for a single dollar. From that game, we isolated the concept of quadratic variation, realizing that squaring the changes is the only way to measure the true accumulated stress and volatility of a path. We then accelerated that game to an infinite speed, carefully navigating the Goldilocks scaling of the bets by the square root of time, which successfully birthed continuous Brownian motion, a continuous fractal, infinitely jagged line of pure mathematics.
We then confronted the reality that this infinite jaggedness fundamentally breaks standard Newtonian calculus because at the microscopic limit, the massive random noise dx vastly overpowers the tiny time step dt.
To survive that mathematical collision, we brought in Kiyoshi Ito's lemma. We utilized the profoundly elegant and now rigorously proven rule of thumb that dx squared equals dt to invent an entirely new stochastic type of calculus. And ultimately, we deployed those new rules to construct stochastic differential equations, empowering analysts to build distinct, highly tailored virtual realities, from Black-Scholes log-normal stock models to mean-reverting CIR interest rate models, simply by tweaking the balance between deterministic drift and random volatility.
It is the mathematical engine that drives the modern global economy. But accepting all of this without challenge would be a failure of critical thinking. This entire structure raises a monumental question, one that we must ask if we want to understand the true fragility of the systems managing our wealth.
I knew you wouldn't let us close the book without finding the structural weak point. What is the fatal flaw hiding in the math?
Think critically about the foundational architecture we have built today. Every single one of these beautiful, elegant mathematical structures, from the Taylor series expansion that birthed Ito's lemma, to the intricate square root floor of the CIR model, to the mean square limit proof itself, they all rely absolutely on one specific, highly restrictive property of Brownian motion we defined back in Part 2. They rely entirely on the property of continuity.
They rely on the foundational assumption that there are absolutely no gaps in the data, that the path, while infinitely jagged and chaotic, is strictly continuous. It traces an unbroken line moving in infinitesimally small connected steps.
Exactly. The mathematics demands continuity, but markets are driven by human beings.
Yeah.
What happens to this pristine mathematical framework, and what happens to the trillions of dollars of derivative contracts priced using this framework when the real-world market does jump?
Oh, that changes everything.
Consider the reality of breaking news. What happens when a stock price doesn't smoothly and continuously glide down from $100 to $50 over thousands of microscopic steps, but instead literally teleports? What if a catastrophic earnings report is released overnight while the exchange is closed, and the stock opens the following morning at $50, completely bypassing and skipping every single price point in between?
That single overnight gap shatters the continuous random walk we just spent an hour meticulously constructing. The mean square limit proof, the Taylor series expansion, Ito's magical rule of thumb, every single one of them assumes smooth, infinitesimal connected changes. If the underlying asset literally teleports across the chart, the foundational assumption of the SDE completely falls apart. The math goes blind.
And that profound vulnerability represents the jagged frontier of modern quantitative finance. The models we explore today are brilliant at managing continuous chaos. But how do you design mathematics to model a universe that is not just highly erratic, but fundamentally violently discontinuous?
That is a staggering reality check to leave on. We opened this deep dive talking about the expectation of absolute precision when dealing with mathematical equations. But diving into these lecture notes reveals that even the most rigorous, heavily vetted, historically successful equations in global finance are ultimately just our best flawed attempts to throw a saddle on pure chaos. Keep questioning the foundational assumptions, keep looking for the hidden leaps in the logic, and above all, keep questioning the numbers behind the world.